says it's loading.
All right, should I start?
Not yet. I will.
Okay.
I got the notification we're streaming, Max.
Okay, great. Looks like we're live. Yeah, Sam, would you please introduce our speaker?
Yeah, so super excited today. We've got Fabricio, who's a professor at UFABC, which, if I am not mistaken, is on the outskirts of Sao Paulo.
Yes.
Currently working with e-graphs for symbolic regression, which is what we're going to learn about today with his colleague Gabriel Kronberger from University of Applied Sciences, Upper Austria. How do? Please take it away.
Thank you. Thank you very much, Sam. And thank you all for having me here today. So in this talk, I'm going to talk a little bit about my joint work with Gabriel Kronberger, that we are actively using quality graphs together with symbolic regression to improve the exploration of the search space. So let me start a little bit about symbolic regression. So in science, we often we start some new discovery by specifying a hypothesis about some phenomena. Then we go ahead and collect some data through experiments and try to describe these measurements with a mathematical function. And we try to replicate that to see if the hypotheses were correct or wrong and needs adjustment. And symbolic regression automates the part of proposing a mathematical expression. So we are searching for a parametric function of this form, f of x and a parameter theta, that describes the observation. So let's say we propose this function here, and this function is applied to the problem of predicting the crop yield based on the temperature. And we can try to apply these same functions to different vegetables, fruits, different crops, and see if it fits well. And this is quite informative for science because we not only can understand better how the phenomena works, but we also can compare the same phenomena for different populations. So in this example, we can compare how the behavior of the spinach and the behavior of tomato differs. So this is an important tool for science. But of course, it's a very challenging problem because one of the things is that since we often search by proposing functions at random, what happens is that it's very easy to generate some over-parameterized functions. So functions that has so much flexibility that can fit any data or almost any data. And we want the function to be as simpler as possible and as strict as possible just to model the phenomena that we are interested in. Also, the search space is not smooth, so any perturbation that we do or applying to a mathematical function can change the behavior of the function in such an extent that it skips from one region of the search space to a completely different region. And also, there's a lot of redundancy, so we can have multiple equally good solutions. So either solutions or functions that are the same function but written differently, or functions that for that specific training data, they describe the data quite well, but when you extrapolate, they actually behave differently. So the solution that we are exploring is the application, the use of e-graphs and equality saturation that can actually help with all of these challenges that we have here. So in the following, I'm going to show 3 different papers that we published recently that all involves the e-graphs and equality saturation in different steps of the symbolic regression search. The first one was this one that we actually, when we start with the idea of applying equality saturation to symbolic regression, that it was a study on overparameterization. So this is a quite simple experiment that we made that basically we depart from this observation that in symbolic regression search, we often have generate expressions that have more parameters than necessary. So here, because of the exponential, we could actually discard this one parameter here that can become another constant and can be fitted separately. So having these redundant parameters creates a lot of complications. First, because the parameters can start to assume different values for the same data. So we have sometimes infinite solutions for optimizing this function. And then we cannot actually interpret the results correctly. And also there's some numerical issues that slow down the convergence of the optimization. So the question here was, is the overparameterization really a problem in symbolic regression? And can equality saturation help to reduce this problem, to mitigate this? And how well does it compare with simpler alternatives such like SymPy? So we test the simplification of SymPy to see how well it fares with equality saturation. And also how fast it is to apply equality saturation. So it's feasible to apply that to a set of different expressions. And what we did here was like we pick a bunch of different symbolic regression algorithms and run them in 2 different benchmark data sets. So we generate a lot of different expressions, and then we apply equality saturation to simplify the expressions with this library called HEG, the Haskell egg, and also simplified with SymPy, and a combination of both. So we apply one after the other. And then we compare the ratio in which the number of parameters of the expressions were reduced by the simplification process. For this problem here specifically, we implement the cost function for extracting the optimal expression from the E-graph as a penalty of 5 for every parameter in the expression and a penalty of 1 for any other symbol. So the length of the expression didn't matter that much, but the number of parameters inside the expressions matter. So it was penalized. And we implemented, of course, a bunch of different rules, equivalence rules, to try to extract the most possible number of redundant parameters. I, of course, will not go through all these rules because it's irrelevant for now. But here are the results that we obtained. So anything...
Fabricio, can I ask one question?
Yes, of course.
You showed the example of like the exponent, and you had like plus some θ3, right? And you can factor it out and presumably collapse it into θ1.
Exactly.
Where is your what equality saturation rule is doing that θ1 times e to the θ3 can be merged into like a new parameter? I didn't really see.
So we could have the maybe it's not here. I don't. Oh, I think it's not here because we actually didn't use a lot of. Okay, I do remember now. This is an old paper, but supposedly, if we did have the rules of exponential something plus something is the multiplication, and then the exponential of a constant can become a constant, we could do it. But in this paper specifically, due to the current constraints that we were facing with the application of equality saturation, one of the things is those situations in which the size of the graph becomes exponentially large. And we were facing this quite a lot in this set of expressions. So we had to reduce some of the rules or cut down some of the rules to be able to run the experiments. But I'm going to talk a little bit about that quite soon. But so for this particular example, yes, there's no rule that could remove this redundant parameter, but we could have. But in any case, with this particular set of rules, we got this result. Anything above the black line here, it means that we actually reduced the number of parameters. Anything below this line, it means that we actually increased the number of parameters. It's quite strange, but SymPy actually managed to do it. So in many situations, we observed that the simplification process of SymPy actually increased the number of numerical parameters somehow, due to some polynomial expansions and some other stuff that they do underneath. But in any case, the quality saturation was quite competent to reduce the number of parameters. And not only that, we also measure how close it was to the optimal number of parameters that we could measure by verifying the properties of the Haitian of the function. And this analysis actually showed us that at most we were like 2 parameters above the optimal number of parameters for the function. But most of the time we actually found the optimal number of parameters using the equality saturation. The problem was how fast it is to apply equality saturation in this setting. Most of the time it was quite fast. So this region here is something below 100 milliseconds per expressions. And of course, depending on the number of nodes, this time might increase, but it didn't increase quite a lot. But there was a lot of degenerate cases here that it took quite some time because some of the rules actually start to increase the size of the graph exponentially. And in some situations, we couldn't even apply equality saturation. So the process was simply terminated because it was using all the memory of my computer. So this was one of the challenges that we had with the eGraph. And this took a little bit of our time because we had to try to find solutions to this problem. And that led me to implement this library here, SR3, that it's a Haskell library for symbolic regression with tree representation. So it's a library composed of many convenient functions and data structures to handle expression trees and create symbolic regression algorithms. Together with this library, I also implemented an eGraph and quality saturation based on HEC and EGG, but with some adaptations to try to mitigate this problem of exponential growth. So in this implementation of the eGraphs, I added some convenient fields for the main structure, convenient for the symbolic regression case. So for example, I have a sorted list of e-classes sorted by the fitness. So I can take something like, let me take the top 100 expressions according to fitness. Also the list of the set of unevaluated e-classes. So eventually what I can do inside the search, I can say, okay, I have evaluated these expressions here, but there are some e-classes that belongs as a sub-expression from some already evaluated expressions that I can eventually sample them and try to evaluate to see if I can find something better. And this is the base of another algorithm that we implemented. We also include the height of the best expression for each e-class. And this is important to try to mitigate the exponential growth. And also some convenient functions to get and set some of the fields. But the important thing here is that we try to mitigate the exponential growth with some limitations of how things are applied. So one of the things...
You've got a question, Fabricio.
Oh, sorry. Yeah, go ahead.
Yeah, I was just wondering, so you have this data and you have a, like, how do you fit stuff? Do you have to like extract out a term and then fit like the term that belongs to that E-class? Or like, I don't think I understand how that could work. Yeah.
Yeah, okay. So the main algorithm, what it does is basically something like this. It creates an expression as expression tree, insert that into the eGraph, and then we evaluate the expression by traversing the eGraph from the root E-class. So maybe I can show the code real quick. It's a little bit messy, but let me see here. It's a tree. Just see real quick.
Well, so if you have the parameters values known, I can understand how you could propagate like the values of sub-expressions up. But like, if you have this, maybe I'm misunderstanding, but if you have an intertwined, like I'm searching for a good expression, but then also searching for good values of the parameters
Okay,
at the
okay,
same
yes.
time.
So in this case, I'm applying automatic differentiation straight from the egraph. So I just I implement this automatic differentiation where I pass the egraph, pass the E-class ID, and then I can calculate the gradient, and then I apply one of the nonlinear optimization algorithms from NLOpt library. So everything is integrated into this library right now.
Okay, so you have an automatically differentiable egraph?
Yes. Yeah.
Okay.
It is a function apart from the implementation of egraph, but it uses the structure of the egraph to, and especially because using the egraph, I can save some computation as I can cache a lot of the evaluation process, especially when I have repeated sub-expressions. So everything is inside this library right now.
Got it. That's cool.
Thank you. Michael?
How does the pruning work when the egraph gets full?
Yeah, so that's what I'm going to explain now. So I implemented a lot of different mechanisms to try to prevent the exponential growth or prevent that the process is killed by the usage huge amount of memory. So one of them is basically one of the processes basically I imposed an upper limit. This is parameterized on the algorithm, but I impose an upper limit for the number of E-classes that the egraph can hold. So imagine that I'm running the quality saturation. What I do is I start running the quality saturation. If it reaches a certain point where it has like, let me say 10,000 E-classes, I stop the process, extract the best expression, and return the current best expression. If I want to restart the process, I can restart from the best expression to try to optimize this expression again. Of course, this is suboptimal, but at least it is preventing this issue with the memory management. This is one of the things I've implemented. Another one is also height increase limit. So if when I am applying a new rule, or I'm applying a rule, a replacement rule in the graph, and the height of the best expression of any node reaches a certain height, this rule is not going to be applied to the graph. So I stop applying these rules that start to expand too much. Again, none of the solutions is actually a solution that they are all suboptimal. They will stop with the guarantee of having the optimal solution. But for practical applications as this one, it's often enough if we don't care much about getting the best possible expression or the optimal cited expression. Another thing is that there's a question, right? So.
Hi, if you're going to talk about this later, that's fine. But I was curious what kinds of rules for causing exponential growth? Is this like associativity, commutativity, or is it other types of things?
Mainly these two, associativity and commutativity. There is also some rules that generate zeros, and these combined with others start to generate something like x plus x minus x plus x minus x plus x minus x, and indefinitely. Actually, this one wasn't an issue because this is a small graph, but there was also some rules, some sequence like 6 or 7 different rules that honestly I don't know why it generates such exponential growth as well. But it is really hard to debug and pinpoint exactly what is causing the exponential growth in this expression in most of the times. That was also one of the reasons that I implemented my own library to try to at least create some debugging functions to try to understand where the exponential growth were coming from, and maybe trying to figure it out the solution to that, or a better solution for that. But mostly it was because of associativity and commutativity.
Thank you.
All right. So another thing that I implemented was the application of the matching rules only if it's causing a merge in E-classes. So if the application of a rule is going to expand or insert new nodes, it's not applied. This is, of course, this is something that should be applied with caution, because at least at the beginning of the equality saturation, we want to keep expanding the E-graph. But at a certain point, we can start just applying the rules that are actually not expanding, but just merging things. This also helped quite a lot in reducing the frequency. So right now at the current implementation, I put here that this reduced the frequency in which the xata induced this exponential growth, but I haven't observed that anymore. So it might still happen, but I haven't actually caught a case that this actually happened. So at least for us, using that for symbolic regression, the problem seems to be partially solved, right? Any more questions about this? Because then I'm going to go to the next paper. All right, so moving along, this is a recent paper from last year that now that we had this library, we start thinking about, okay, what else can equality graphs bring us to improve the search for symbolic regression? So in symbolic regression, there is this concept called neutrality, that whenever we are applying some search algorithm, we often apply some perturbations to the expressions to propose new candidates. And many of these proposals can actually be neutral. For example, here we have this expression here, and we make this perturbation here that it's basically the same expression, right? And while this makes the search space quite redundant, on the other hand, is the one thing that enables us to navigate the search space. Because what happens is, if we propose something new that is a larger expression, but is evaluated to the same evaluation function, to the same loss, then we can keep accepting these perturbations and navigating throughout this region of neutral perturbations until we find a point where we can escape to a better local optimum. Because if we didn't have this kind of situation, what happened would be, all right, let me propose something new. It's worse than the current candidate, discard. Propose something new, it's worse, discard. And we keep discarding, and we actually never move from the current local optimum. So, of course, the neutrality has the implication that while it helps us to navigate, it's also a waste of evaluation, because we cannot know whether two expressions are the same thing until we evaluate them. So this wastes a lot of generations just traversing this neutral region that actually doesn't actually need to be evaluated. So ideally, we should be capable of detecting the neutral zones, generate this neutral perturbation somehow, and create or detect the escape regions where we can actually get out of this neutral space. And then we came up with the eGGP, eGraph genetic programming, that is basically a genetic algorithm that goes through the process of create a list of random solutions, and for each solution applies a perturbation, recombination, and then applies some selection to replace the current population, and keep going like that. But this version here has two main differences to the traditional GP. One is that we keep the whole search history in memory. Every single solution that we proposed is put in a single eGraph. So now the eGraph doesn't hold a single expression, but all the expressions that we have visited. It's all in the same eGraph. And using this eGraph, we propose a modified crossover and mutation that can actually enforce the generation of a unique solution, a solution that was never visited before. And the way we do it is something like this. Let's say we have this E-graph. The things in green are the root of the expressions that we actually evaluated. And let's say that we pick this expression here, the x plus x, oh, no, sorry, x plus square root of x. We pick this one expression to mutate, and we pick this region of the expression to mutate and replace with 2 times x. But when we generate this expression, we can query the graph and see, okay, we actually have this expression here. It's x plus 2 times x, and it was evaluated already. When we detect that, we take this newly generated expression, the 2 times x, take the root of it, and replace with something that is going to generate something that is never new. And we can do that right away with the graph because we simply try all the operators here instead of multiplication and query whether this sub-expression belongs to the graph. If it doesn't belong, it's a candidate. We can apply the mutation from there. So with this, we can actually enforce the generation of something that was never observed before. For the recombination that we take 2 expressions and try to recombine, what we do here is basically this. We pick the first expression to be combined, in this case, again, x plus square root of x, and we choose the second expression to recombine, x plus 2 times x. If we choose to replace this square root of x with anything from here, we have a lot of selections. We can replace this with this whole expression, with x, with 2 times x, or with 2. It's all the sub-expressions that we have here. And we can actually do all of these replacements, and before evaluating the expressions, we can check which ones generate something that is not contained in the graph. And then we sample just one of these candidates and do the evaluation. So by doing this, we can actually enforce that the search is guided by novelty as well, not only by the pressure of generate something that is either the same fitness function or the same loss function or something better. And by doing this, this is one of the comparisons that we made with a lot of state-of-the-art algorithms. So basically, this is ours, and this is the current best algorithm. So this plot here says that they are equivalent. And for the remainder, they, in these 2 cases here, they may not be equivalent. They may be better than these 2, and they are definitely better than these other algorithms. But with another nice property that we generated the smallest expressions compared to the other algorithms, except this one, but this one also produces very much worse results in accuracy. So now we have an algorithm that can find an equilibrium of the top accuracy and good model size. So the functions are simpler and yet accurate. All right, any questions about this one? All right, so another consequence of doing this algorithm is that, and together with the library SR3, is that we created this tool called Reggression with 2 Gs. That is some sort of a database of expressions that can be used to explore different hypotheses. So let's say that after we finish running this eGGP, we save the current state of the eGraphs into a file. So basically, it's kind of like an eGraph that have all of the explored expressions, and it can serve as a database. By exploiting all the nice things about the eGraphs, I can do some query-based approach on this eGraph. So I can have a pattern matching ability. I can explore the building blocks that is contained in the eGraphs. I can detect modular expressions. I'm going to show them all here and do a bunch more. So Let me go through a simple example. So let's say that I have this function, this data here, and I use the red part to training, and the green part is just the test data set. So it's a very difficult data to fit because we don't know the behavior of these outside regions. So it can be anything, and we can find many different proposed expressions to fit this data. And then we run the eGGP. Just a curiosity, the eGGP is currently installable by pip as a Python front end to the Haskell code. So everything is Haskell underneath. So essentially what I did here was run this algorithm and store the final egraph into this flat EGG. And then I can start up the regression library and create this egraph in memory. And one of the things, the one obvious thing that I can do, of course, it's nothing special. I can, for example, retrieve the top 5 expressions, and it's going to return something like this. The expressions is LaTeX code, the fitness function, and the size of the expression. But then we can see if we plot these expressions that even though they are quite similar in the training set, they diverge on the outside of the training region. So we can try to make a little bit more of exploration, right? So for example, let's say we want to get the top 10 expressions, filtered by all the expressions that have size equal or smaller than 10. We can do that right away, exploiting the egraph. Another thing that we can do is get the distribution of the tokens. So basically what I'm doing here is take the top 1,000 evaluated e-classes from the egraph, and then I'm counting the occurrence of each one of the symbols in all these expressions and calculated the average fitness of them. So for example, the variable x appeared more than 2,000 times with an average fitness of this one here. Absolute function. So this is the V0 here. It's kind of like a match all pattern variable. So the absolute function appear 400 times and with this average fitness. So this is some way to extract some information about the search space to say, okay, maybe this function here is more likely to help us to produce some new expression that it's can be good, right? For example, the cosine here it seems to be very competent and was very well explored. On the other hand, the exponential was barely tested, but mainly because it induces something really bad here, a worse average fitness than the others. And of course, one curiosity is that the data set was generated by exponential function, not a cosine or a sine. But the thing is that the exponential is very difficult to fit using nonlinear optimization. And then it's very often that we try an exponential function, it gives us a bad loss function, loss value, and then we discard that, right? But we can also try to explore the solutions that uses the exponential. And we can say something like this. Let's say, I want to get all the expressions that contains the pattern e to the power of something times something, right? So this here is the pattern match all variable 0, match all variable 1. So we can apply this command here, get the top n expressions with the pattern x of v0 times v1. This is going to extract all of the expressions that contains this pattern. So this pattern doesn't necessarily need to be at the root of the expression. It can be inside the expression as a sub-expression. And it's going to filter down all those that are actually evaluated and then return the top n of them, right? And we can also add some parameters, for example, to say, okay, I want to specify that this specifically should be the expression at the root, or I want to get the top n expressions that does not contain this pattern. So we can do this all with this library here. Another cool thing that I can do here is I can run a different algorithm, not only HGP. So here I'm running Operon, and I create a CSV file containing the expression and the fitness function. And then I can insert that or import that into the eGraph. And by doing so, I can run again the top 5 expression and do all the analysis to see if the other algorithm could find a different solution that is better for us. I can also manually insert any expression. So we can see here that it's quite easy to write an expression. So it's basically a simple notation where x something are the variables, x0, x1, x2, etc. T something is the parameters, theta. And okay, then that's it. So I insert that and it automatically going to calculate the fitness and estimate the parameters. So we have here that the true expression that I just inserted here that was used to generate the data set has a better fitness than all of the expressions that we tested so far. Other things that we can do, we can load up the regression without any expression. So I just created an empty eGraph, and then I can insert different expressions into the eGraph. Okay, so I inserted this one here, x plus 3 squared minus 9, and x times x plus 6. They are the same, they are equivalent, right? But initially they have e-class ID of 6 and e-class ID of 9. But then I can run the equality saturation and apply the set of rules, right? So basically, if I do this, EGG, x at 5, and then I can query again the ID of the expressions that I just inserted. And now the ID is going to be the same. So we can actually run the equality saturation and see whether 2 expressions are equivalent. Another thing that I can do is get the n equivalent expressions for that particular e-class ID. So it's going to return, in this case, the 10 expressions that can be extracted from this e-class ID. So we can see all the equivalent ones here. 6 plus x times x, x times 6 plus x squared, and etc. And now we are working on trying to figure out how to exploit the eGraphs to measure the structural similarity. So one of the things that we are currently investigating is, for example, we have these 2 expressions here, x0 plus x1, x1 plus x0 times x1. And we can try to ask, okay, how similar are these expressions? We could apply something like a 3-edit distance that would say something like, okay, we have to maybe swap these 2 children, so one operation, and then we should add the multiplication and another x1, so 3 operations. But we all know that x0 plus x1 and x1 plus x0 is actually the same thing, so they shouldn't be accounted as something different. So what we can do here, we can insert both expressions, calculate the equality saturation, and compare the e-classes IDs of all the subtrees of both expressions. And then we can say, okay, this expression here contains this e-class ID here. And we can calculate some sort of Jacquard distance, for example, between expressions. All right, so this is about what I had to show today. Very summarized, but there are many details that I couldn't bring here today because it would take a lot of time to dig in. All the things that I'm doing are in PIP or open in a repository. Like I said, all of them uses this SR3 Haskell library as the base library to implement the main algorithms. And these algorithms are implemented in Haskell that compiles to a Python library that it's available for Linux, Mac, and Windows. Okay, so that's about it. Thank you very much. And I think we can open for questions and discussions. Thank you. Thank you very much.
Thanks so much, Fabricio. It was cool. Really cool to see like real usage as well.
Yeah, this was very cool, Fabrizio. I know that I suspect Saul will have some questions once they get around to it, but the Python bindings look very cool. It's very cool how you are, visualizing the plots. I'd like to start off with a question. So in your the terms that you're representing in your e-graphs, you have functions and variables and parameters. Parameters are interesting in the sense that they are the things that you are learning. Sort of, I guess I have several questions about parameters. Is the actual regression, the learning of the values for parameters, happening inside the eGraph, or are we using an external tool? And then the second question is, say I have an E-class, right, which has many, many terms in it, of course, which mention parameters. Am I limited to, like, does that E-class represent a particular learned value of those parameters? Or are we sort of pre that, or could we represent many possible learnings of the parameters?
Okay, so about the first question, maybe now I can share this other screen here of the code. What I have here, so there is some steps to the process of learning the parameters, right? First, I have to define the loss function. In this case, we are using the likelihood function. And basically what I do here is this function build NLL. It's actually building an eGraph that takes the current expression and envelops into a new expression that contains the calculation of the likelihood. So the result of this is the eGraph in which the root is the likelihood function with the model that I'm investigating. So this is one step. And then what happens here is that let me go back here. Let's see if this one here. No, there's other one here. So I pass this along to this function called minimize NLL eGraph. So again, I'm passing the eGraph that contains the instructions on how to calculate the likelihood, right? And together with this one, I also have this grad NLL eGraph that is an eGraph that calculates, given a set of parameters, given a vector of theta, it calculates the likelihood function and the gradient. And then I pass this function here to this wrapper, to the NLOpt library that has nonlinear optimization functions to optimize the function. What happens here is that this grad NLL eGraph is a function that takes the eGraph and can calculate the automatic differentiation of that to have the function values and the gradient, and then can be used to the NLOpt. So while the evaluation of a proposed theta is done inside the eGraph and its corresponding gradient, the optimization process is an external library. So that answers the first one.
Okay. I guess one follow-up on that then. I guess, so one, this is very cool. Much more sort of, I guess, calculation is happening inside the eGraph than I first considered. But it sounds like at some point you have to eventually call out to some external optimization solver to do this. And is that, I guess, I think you just said this, but I maybe just lost the thread. Like, at which point are you? I mean, presumably you're doing all of this in the eGraph for some reason, meaning that like you get benefit from the caching or the different redundancy elimination, and that's amazing. But at some point, you have to get out and pick some non eGraph thing to send to the solver. Where is that point where you come out of the eGraph?
So actually, what comes out from this grad NLL eGraph?
Mm-hmm.
So again, this takes the eGraph as a parameter and the proposal of a theta, and I evaluate everything inside the eGraph. And what comes out is a scalar value, that is the likelihood function, and the vector of parameter values. So that's the one thing. So basically, what I have to pass to the solver, to the nonlinear optimizer, is basically a function that given a theta is going to return these values for me. So I actually don't need to materialize something outside the eGraph except for the evaluated values. So everything actually happens inside the eGraph.
I see.
I never have to deconstruct. In the first version of SR3, I actually did this. I extracted the expression tree, that is the optimal expression for that E-class, and then I apply automatic differentiation and pass to the optimizer. But after some time, I realized, okay, I'm wasting computation by doing this. I have some overhead. And second, I could just exploit evaluating things inside the graph, because if I have common substructures that don't have any numerical parameters, I can evaluate one and have already that cached somehow. And while this in practice didn't give me that much optimization, computational optimization, but it helped a little bit. It helped a little bit.
Very cool. Okay, so quickly to part two, because others probably have questions. You know, this is like nonlinear optimization. It could be wildly complicated, and it seems to me that there might be many, reasonable local minima or whatever for your parameters. And are you just picking one, or can you handle the fact that there might be multiple?
Yeah, that actually happens a lot. So what I do here is inside the algorithm is I run the optimizer many times and pick the best solution. So I restart with different initial conditions for the theta. But if I just run once, then yes, I'm going to commit to the local optimum that I reach.
I see.
Other solutions is to use a global optimizer, but they are quite expensive, and so it's not actually worth the price that we have. And about your second question, let me show you here. So this is the eGraph data structure. And each class, let me go here, wait, here. And each class has this info field assigned, and the info field has here the parameters. So the vector of parameters is assigned to each class. So even if I have two expressions that share some common expressions, what is going to dictate which are the theta parameters is the root of the class. They're going to store the optimal parameters for that expression. And always for the smallest expression that can be extracted from that E-class. So that's another cool thing, that eventually, if I apply quality saturation and merge two E-classes, what I do here is that I always keep the parameter vectors of the smallest one. And if the smallest one doesn't have this information, because let's say I have evaluated the largest one and the smallest one that was generated by quality saturation doesn't have this information, I then prompt the algorithm to refit that and replace the parameter vectors. So I keep the consistency that whenever I run a quality saturation and merge things, I enforce that I will either keep the smallest parameter vectors because it's the smallest expression, or I refit to get the smallest one.
Interesting. Okay, thank you.
Thank you.
I wanted to ask, you talked about trying to debug the eGraph explosion. You added some specific features. Are there any like specific features that we might be able to bring over to egg and egglog, for example, that helped?
Yeah, so at that time, Hack didn't have the bug part. It was even something that I created an issue on the GitHub repo to try to implement that. But eventually what happened, I was actually committed to try to implement something to contribute to Hack, but eventually I felt that I need to understand more how the quality saturation process worked. So that was another reason in which I actually implement my own library. But the library is heavily based on Hack. So if you make a code comparison between both, they are very different. There are a few things that will strike resemblance, but it is the logic behind it is almost a direct translation from Hack. And also another thing is that since Hack is for general purpose, I want something that I could optimize for specifically this use case, like inserting new expressions, inserting new fields into eGraphs like the parameters, etc., and create some specific kind of rules. For example, I also implemented bidirectional rules and some other kinds of conditionals for the rules that is based on certain properties of symbolic regression models. I have also the intention to implement something like, okay, let me see whether I can infer that this expression is always monotonically increasing. If I can guarantee this property. This is also intended, so I also kind of prepared the code to accommodate for that as well. But even so, I still actually use Hack for other applications. For example, I have a student that used Hack to optimize programs generated by a program synthesis algorithm. And it performed quite well. And now that they have a lot of different ways of debugging it, sometimes I actually use that to even debug some things that, some bad things that happens in my own code. So I take the same expression, I take the same set of rules, implement it in Hack, and try to figure it out whether I can find the reason of any exponential growth. But again, the history is that when I started doing this, Hack still didn't have that much support for debugging. And I also wanted to learn more about the process, so I felt motivated to implement. But then again, I think Hack is a very interesting library, and people that at least like to program in Haskell should use more often this one.
I have a like
Oh,
a little.
go ahead, Saul.
Oh yeah, just to follow up on that. I know one of the things in Egglog we're trying to add to help with debugging is like proofs, so that like right now I just have to stare at eGraphs and try to see what changed and trace things. Is that something that you use in Heg to narrow down like why, what was the sequence of rules that got you to this large term?
Well, the way I'm doing right now is a very crude form of debugging. So yeah, I basically store the history of applications of the rules and which rules led to a specific new E-class. And at the same time, I try to do other things like detect growing E-classes so that I can focus the debugging only on this part, and also some rudimentary form of detecting loops in the eGraph. But then again, none of them is perfect, but it kind of helped me a little bit. I also have a student that is implementing some integration with .vis to try to visualize process step by step that is happening inside the equality saturation. But this one is going to take a little bit of time, I think.
Very cool. Thank you. Yeah, and if you end up using this egraph serialized format, which is in JSON, has some .viz and also interactive viz support. If that's useful to look at or use, it should be agnostic to like where the egraph came from. Yeah.
Do you have a link for that?
Yeah, I can put it in the chat.
If you can say, oh, thank you, because I definitely going to look at it. It is something that the student of mine actually thought about making some sort of JSON format for the graph, so it can be interchangeable. But if that already existed, even better. I wasn't aware of that.
Yeah, and contributions are definitely welcome to that. Like there's visualization code from there's some code to analyze those JSONs written in Rust, but we can add more. The nice thing about the format is it's that it's a format. So
exactly, we can expand the current set of libraries that are available for that. I think that that's quite cool.
Okay, well, we are at time. Thank you, Fabricio, so much. This is very cool. I've posted some of the links to your stuff in the Zulip. I'm not sure if you're on the Zulip, but folks might have follow-up questions, in which case they might post it there. You can also just reach out to Fabricio directly.
If you can send me the link of that, I can go there.
Yes, I will do
check
it
for a follow-up
right now. Here is the Zulip thread we are in.
Perfect. Okay, so I'll be sure to have a look there if anybody has any questions.
Awesome. And yeah, feel free to, be sharing what you're up to. This was all very, very interesting. And I'm definitely going to be checking out the code.
For sure. Thank you very much.
All right. Thank you. Bye, everyone.
Thanks, guys. Bye, everyone.
Bye.